So today we're going to talk about linearization and also differentials, two similar but different things, okay? So we're looking at these two curves right here, okay? And this is going to be my function f of x. So let me label that. This is going to be f of x, okay? And this point right here is at a. So this point would have to be a comma f of a. And so what I want to tell you is that this right here is the tangent line to the function at x equals a. Okay, so this is just simply the tangent line at x equals a. All right, and we are going to call this tangent line L of x. And we also know the slope of this line would be the derivative at a. Okay, so slope would equal f prime of a. So what I want you to understand is that at exactly this point of tangency right here, the function and the line are exactly the same, but only at this point. So what happens is we really close. If you look right in here, you can't tell much of a difference right here and right in here. You really can't tell much of a difference between the function and the tangent line. So like I'm talking about like right in between my fingertips right here, there's not much of a difference between them. So like right in this region, we could use the tangent line to predict function values. So a linear equation is much easier to work with, all right? So right around the point of tangency, L of x is a good approximation, okay? So we say L of x is a good approximation of f of x for values very close to x equals, in this case, x equals a. All right. So as we move away from that, either to the right or to the left, okay, right here's the actual function value, and right here would be the approximation. Okay, so this would be the approximation at this x value, but this gap right here, that difference between the two is called the error in the two. All right, and so even further out here, this is the actual value, and I'm trying to line this up. This would be the approximation. There is a huge error. So I want you to understand that the further we get away from this point, we cannot really use the tangent line to approximate the function. All right, that's actually part of what calculus BC is. So instead of a line, we start wrapping polynomials around this thing, all right, and we get a better and better approximation. But that's second semester calculus in college, okay? So this is the error, all right? And that's not easy to do, by the way, all right, to start wrapping this, okay? All right, so a few things we need to know to come up with the equation of the tangent line. Okay, we're going to use point slope form. Okay, so y is equal to m times x minus x sub 1 plus y sub 1. Okay, where the slope of our tangent line is going to equal m, which is actually in this case going to be f prime of a. All right, and we're going to have a point, and I'm going to label that point x1 comma y sub 1. In this particular example, it would be a comma f of a, okay, for this line right here. All right, so all of this becomes y equals, instead of slope, we could write f prime of a times x minus a plus f of, and my y1 is f of a. That's the y coordinate at x equals a, all right? And really what we do is we got to figure out f of a, right? And we got to find the slope there too, okay? And we call this the linear approximation, so we call it L of x. So we use L of x instead of y here, okay? So L of x is equal to f prime of a times x minus a plus f of a. I want you to understand this is just the equation of the tangent line. And we've been doing that for a long time. I mean, since September, okay? And it's at, in this case, at x equals a, all right? Okay, so to do this linearization, okay, there's two things we need. We need one, the point of tangency. Anytime to write the equation of a tangent line, we need the point of tangency, which would be the a comma f of a. That's called the point of tangency. That's where the tangent line is touching the curve, all right? And the second one is we need the derivative at x equals a, and that is f prime of a. Okay? So here's the next problem. We want to find the linearization of f of x, which is equal to the square root of 1 plus x at x equals 0. Okay, so that is going to be my point of tangency. It's going to be x equals 0. Okay, and then we're going to have to put 0 into the function and see what the output is. Okay, and then we want to use it to approximate the square root of 1.02. Okay, so what we're going to do, this is the square root function, all right? And usually if we rearrange this from last year, the square root of x plus 1, so that would cause it to shift to the left 1, right? It usually starts at 0, 0, so it's going to start at negative 1, 0, okay? So I'm going to draw a quick little sketch so you understand what we're doing, okay? All right, so here's the function. It looks like this. It starts at negative 1, 0, and remember, it comes up like this. Something like that, right? And this point right here is negative 1 comma 0. Right here, this point right here, and let's go ahead and find f of 0. Okay, so f of 0 would equal the square root of 1 plus 0. Well, that's just the square root of 1, which is 1. So this point right here is the point 0, 1, all right? And what we're going to do, this is our function, this is the f of x, okay, and it's definitely not a line, all right? But what we're going to do is we're going to find the tangent line at x equals 0. So right here, x equals 0, and I'm going to do my best to draw my tangent line, okay? And there's my tangent line, and this is going to be L of x, all right? And we're finding this tangent at x equals 0, so that's why I drew a point of tangency right here, okay? And then we're going to want to use this approximation to find the square root of 1.02, and I'll talk about how we're going to do that in just a minute, okay? All right, so we have our point. The point of tangency is the point 0, comma 1. Maybe I should label that point of tangency. All right, and now we need to start finding the derivative because we need the slope of this, okay? So we're going to need to rewrite f of x. So instead of the square root of 1 plus x, I'm going to write it as 1 plus x raised to the 1/2, which is going to allow me to take the derivative. So f prime of x would be 1/2 times 1 plus x, subtract 1 from the power, so that would give me a power of negative 1/2, and then times the derivative of the inside here. So the derivative of x would just be 1. Okay, so we don't really need to write it. Okay, you could if you really wanted to. All right, so then that means f prime of x is equal to, this just becomes 1 on top, and the bottom is 2 times 1 plus x to the 1/2 power, or 1/2 square root of 1 plus x. You could write it either way, okay? Now, what we want is this is a rule that will give us the slope at any point, right, on the curve, but we want the particular one at 0 because we want the slope of this tangent line, okay? So we want to find f prime of 0, and that would be 1/2 square roots of 1 plus 0. Well, 1 plus 0 is 1, and the square root of that is 1. The slope here is 1/2. So I know my slope is 1/2, which I'm going to start writing my equation. So L of x, my linear approximation, is going to be the slope, which in this case is 1/2, times x minus 0, because that's the x coordinate of my point of tangency, and then plus 1. I'm going to clean this up, so L of x simply becomes 1/2 x plus 1. And that's really easy to calculate compared to the square root function, okay? All right, so we found this derivative at x equals 0, okay? So what does x need to be in order to make this become 1.02? Okay, so we're gonna use this. We need to know what is the x that I could put in here that would help me to approximate 1.02. So you can look at it a couple of ways. Okay, so I'm gonna do it kind of, I think, the harder way. All right, but it's more mechanical. Is you can write this: when does the square root of 1 plus x equal the square root of 1.02? And some of you may be able to just go, oh, it's this number, and that's okay. All right, so I'm going to square both sides, and that means 1 plus x is equal to 1.02. Subtract 1, and you get x is equal to 0.02. So, all right, so my x, okay, and this should make sense, okay, now that you see it. Oh, 1 plus 0.02 is 1.02, right? There's my 1. That's the one right here, okay? So what this x is the decimal after the 1, okay? So that's why this came out to be 0.02 or 0.02. Now, where did we find the point of tangency? We found it at x equals 0, right? We based this whole linearization, this linear approximation, at x equals 0. Well, heck, that's 2/100ths away. That's darn stinking close. Okay, so this is going to be a good approximation. Okay, so I doubt any of us could, without a calculator, tell me what that is. Okay, with pretty close to it. Okay, I mean, it's going to be, we should realize it's going to be, since that number is close to 1, the square root of 1, which is 1. So our output's going to be close to 1, right? Okay, so what this means is that f of 0.02 is equal to the square root of 1 plus 0.02, which is the square root of 1.02. Okay, so we're finding f of 0.02 to get the square root of 1.02. All right, using our linear approximation, okay, we want to actually find f of 0.02. And this is going to be important. Don't put an equals here. They'll mark it wrong if you put an equals, because this is all about approximating. So that this is the only place where you have to put the approximation instead of equals, okay? So f of 0.02 is approximated by L of 0.02. They are close to the same because I found this point of tangency at x equals 0, and what I'm putting in is close to it, okay? So that means the square root of f of 0.02, which is this also the square root of 1.02, is 1/2 times 0.02 plus 1, or half of 0.02 is 0.01 plus 1. So a good approximation is of the square root of 1.02 is 1.01. Now I realize most of us would have said, oh, it's close to 1. Yeah, but you didn't know how close it was, right? You probably didn't know 0.01, all right? Okay? All right. So that's how we're going to do it, okay? If we want to approximate, and this is going to be on your final, okay, where you have to approximate something and come up with the tangent line. So basically all you really have to do, okay, is find the tangent line and then plug the x value in that I'm trying to make you find it at, okay, to approximate, all right? Okay. We're going to do another one that's similar to this, okay? This is a little bit hard because it's a little bit harder because you had to find the 0.02. You had to figure out what x do you put into this function. Usually it would be just the square root of x, okay? Usually it's something, just a simple function. All right, now, the other thing for homework is, and you're not going to need to do this for the final, okay, or the AP exam, I want to calculate the error. So how far are we off from the actual value of the square root of 1.02 to this approximation? Are we close? Is this an overestimate or is it an underestimate? Okay, so I want to find our error. How far are we off? okay? And the error, okay, so let me go back to the first page really quick. The error was this right here, this vertical distance between the actual function value and the approximation. Okay, so to calculate this error, all right, how far we're off from the actual value is we're gonna take f of 0.02, the actual value, and we're gonna subtract L of 0.02. All right, which is equal to, now we're gonna need a calculator to do this, okay? This would be the square root of 1.02, because if you put 0.02 into the function, you get 1.02. And we already calculated this is 1.01. And so we're gonna need a calculator. I'm just gonna grab my calculator really fast. I thought it was right here. Oh, hold on guys, sorry. Okay, so in our calculator, we're gonna type in the square root of 1.02 and then minus 1.01. And we get negative 4.95 times 10. That E means times 10. So this, it kicked it into scientific notation. So that means this is either a really big number or a really small number. Because the exponent's negative, it's a really small number, okay? So this is equal to negative 4.95 times 10 to the negative 5th power, okay? Which turns out to be, okay, negative 0.0004, no, sorry, more zeros. 5 and then 495. No. $495 there, sorry. Yeah, okay, sorry about that. Oh, sorry. Okay, that's stinking small. Okay, now this is important. The sign is gonna matter, okay? So which one's bigger? If we're subtracting these two numbers, right? Which one's gonna have to be bigger and which one's smaller, okay? So this L of X is gonna have to be bigger, right? Because we're subtracting, like think about this, 3 minus 5, that's gonna give you a negative value, right? So we got a negative value here, all right? So L of X is bigger than the actual function, okay? So what this is L of X, or L of, I shouldn't say L of X, L of 0.02, okay, is an over estimate. And the reason I know that, it's because it's an overestimate because L of 0.02 is larger than F of 0.02. Okay, so if this had come out to be positive, then L of X would have been an underestimate, which means L of 0.02, I keep saying L of X, but I mean L of 0.02. L of 0.02 is below it, because when you take a higher number that's above it, F, and you subtract a lower number, L, then that's gonna give you a positive value, okay? All right, so that's how you do this, okay? Okay, the big idea. So I'm doing this because the homework asks you specific questions like this, okay? Don't get hung up on it. What's important, the most important thing is you come up with an equation of a tangent line, and then you plug your function value that you're trying to find the function value at into the linear approximation and see what number you get. That's what's important, okay? So for this next problem, we want to find the linearization. Basically, that means tangent line, okay, of f of x equals cosine x. And we want to do this at x equals pi over 2. And then we want to use it to approximate cosine of 1.75. So this is what I'm saying. A lot of times it's just x, right? And so we're going to put 1.75 into our function. We're also going to put 1.75 into our linear approximation, okay? All right, so we want to find cosine of 1.75. So let me tell you, pi over 2 is about 1.57. So we're finding the tangent line at 1.57 and roughly, okay? And we want to find, we're going to approximate 1.75. Okay, 1.75 and 1.57, those are pretty close to each other, okay? So the linear approximation is going to be pretty good to the actual function value, okay? So the very first thing is we got to find the point of tangency. So that we got to find f of pi over 2. And f of pi over 2 would be cosine of pi over 2. Okay, so pi over 2 is on the positive y-axis, right? I'm going to do it up here because I know we're not the best at this, okay? So pi over 2 is right there, okay? Right there, my x is 0, my y is going to be 1, and my r is going to be 1. And the cosine ratio is x over r, so 0 over 1. So that makes this equal to 0, okay? Now, we got to find the derivative of f of x. So f prime of x. So the derivative of cosine x is negative sine x. And now we got to put that pi over 2 into this. So that'd be negative sine of pi over 2. And luckily we can use the same diagram because that's still angle pi over 2. So my y is 1 and my r is 1, right? Because sine is y over r. So 1 over 1 is 1, but I have a negative in front. So this becomes negative 1. All right, so my linear approximation is L of x is equal to my slope, which is negative 1, times x minus my x coordinate of my point of tangency, which is pi over 2, and then plus 0. Okay, so this, simplifying this, L of x becomes negative x plus pi over 2. All right, so f of 1.75 is equal to cosine of 1.75, because whatever you put in the function, you put in the cosine, right? Okay, so that means f of 1.75 can be approximated with L of 1.75. And so f of 1.75 is negative 1.75 plus pi over 2. All right. And so this becomes negative 1.75 plus pi over 2, which is approximately negative 0.179. All right, and I put that into my calculator. All right, so f of 1.75 is approximated by L of 1.75, which is negative 0.179, okay? Now, let's find the error. So the error is the difference between the actual value, so f of 1.75, and my approximation, so minus L of 1.75. If this comes out to be positive, this one's bigger, and then L of x will be an underestimate. If f of x is smaller, okay, then this is going to come out to be a negative value because this one's bigger, all right? And then we'd come out to be a negative, all right? So this becomes cosine of 1.75 minus, and I'm going to put, this is the exact linear approximation, so minus negative 1.75 plus pi over 2. And so I'm going to put that into my calculator, my handy dandy calculator. Bop, bop, bop. Remember Blue's Clues? All right. Okay, I need some sleep. All right, so cosine of 1.75. You think I'm the weirdest math teacher ever. Okay, minus negative 1.75 and then plus pi over 2. And just checking to make sure I put everything in my calculator right. Okay, so we get, okay, darn physics. I knew this is the wrong answer, okay? Because that's not a very good estimate, right? Okay, here's the problem, and we got to be careful, especially for the final. I'm going to remind everybody, okay, that's taking physics and calculus, because there's quite a few of you guys, so that's cool you guys are doing that. The degree, we need to be in radians, okay? So I need to switch my mode. You know what? I'm actually glad I did that. I feel stupid, but I'm glad I did it. Okay, so now let's put it in, we get the right answer. Yeah. So 9.576 times 10 to the negative fourth. Okay. So basically 9.5, yeah, 9.576. 9.576 times 10 to the negative fourth. Now that came out to be positive. Now the only way this comes out to be positive is if the F is larger than L, which means F is above. So that means L of 1.75 is an underestimate. Okay, so this is an underestimate. Because, all right, and what we know is F of 1.75 is greater than L of 1.75. And because this one's bigger, when you go to subtract it, it's going to come out to be positive, which the 9.576 is positive. Whew, okay, here we go. Let's do the next one, okay? So let me pause this. All right, this is actually more like what you're going to see on the AP exam in my final, okay? Find an approximation for the cube root of 1 minus x for x really close to 0, okay? And then you'd say something like this, then use it to approximate x equaling 0.02 or something like that, okay? So we want to let, and I would write this, let f of x be this approximation, okay? So cube root, or not approximation, but this function, cube root of 1 minus x. Okay, so we want to find f of 0. And so that would be the cube root of 1 minus 0, which would be the cube root of 1. And the cube root of 1 is just 1. So my point is 0, 1. All right. And now I need to find the derivative, okay? So I'm going to rewrite my function as 1 minus x to the 1/3 power. So that means f prime of x is equal to 1/3 times 1 minus x. I got to subtract 1 from that, so that's going to make negative 2/3 times the derivative of this inside function, which is negative 1. Okay, so f prime of x, cleaning this up, f prime of x becomes negative 1 over 3 times 1 minus x to the 2/3 power. And so f prime of 0 would equal negative 1 over 3 times 1 minus 0 to the 2/3 power. Well, that'd be 1 to the 2/3 power, which is 1, because 1 to any power is 1, times 3 is 3. So this turns out to be negative 1/3. Okay, so we have our slope, we have our point, we can go for our linear approximation. So L of x is equal to negative 1/3 times x minus 0 plus 1. X minus 0 is just x, so L of x, okay, is equal to negative 1/3 x plus 1. Okay, so what this means is that the cube root of 1 minus x can be approximated with using negative 1/3 x plus 1. But your x values have to be close to 0. And the closer you are to 0, the better the approximation is, okay? And the further away you get, the worse approximation, okay? Nobody asks you, like, how far can you go out? That's actually Calc BC, okay? How far can you go out, all right? Okay, guys, that's it for this part. Now we need to talk about differentials, which is probably the easiest part to understand. All right, so we're going to talk about differentials now, okay? And what are differentials? So when we see dy just by itself and also dx, these are called differentials. Okay, now what happens is dx is really this. Dx is really the limit as delta x approaches 0 of delta x. Okay, so what happens when you're changing x? So right here is my change in x. What happens when that gets really, really close to 0? So this is just infinitesimally small is what it is, okay? And dy is equal to the limit as delta y approaches 0 of delta x, okay? Or delta y, whoops, delta y. So here's my delta y. So if we shrink these down, okay, and this, if you make one go to 0, the other one goes to 0, because you're making this point get closer and closer and closer and closer and closer to this one, which, can you see the dy is, or the delta y is actually shrinking too? So if you shrink one, you're going to shrink the other, but how much do you shrink the other? And that's really what this is all about, okay? So this delta x actually becomes dx when we get really, really small, and the delta y becomes dy, okay? So that's why slope is delta y over delta x, and in calculus, it's dy over dx, all right? Okay, so here's what happens, okay? We want to find the differential dy, okay? And the way we do this is, all right, at x equals 1, this is what it's saying. If we change x by a little bit, 0.01, how does that affect the y? So how much does y change by, okay? And it depends on the function, okay? So this is how we're going to find the differential dy, okay? It's really quite easy, all right? So what we're going to do is we're going to find dy over dx. So dy over dx is equal to, and this would be x to, so dy over dx would be 5x to the 4th. I started to rewrite the function again. 5x to the 4th plus 37, right? That's all it would be, okay? Now, how do you find this dy? Well, the way you find the dy is you multiply both sides by dx. It's as simple as that. And dy is equal to 5x to the 4th plus 37 times your dx, okay? And you need to have the parentheses around the 5x to the 4th plus 37, okay? So the dy, how much the y changes if we change the x, okay? How much the y changes is dependent upon the x you pick, and also how much you change the x, okay? So how do you find this dy? So we want to find, okay, if x equals 1 and we change the dx just to 0. We change it by 0.01, how does that affect the delta y, okay, or dy? So dy is equal to 5 times, and my x is 1, so I'm going to just put 1 in here, to the 4th plus 37, and then times 0.01. This is putting 1 into this expression and my dx in, okay? So dy is equal to, this would just be 5 plus 37, or 42, times 0.01, okay? And so my dy in this case, if I multiply those, I get 0.42. So if I'm at, this is what this is saying is, if I'm at x equals 1, and I just change my x and increase it by 0.01, okay, that's going to result in y changing by 0.42. So it's not going to change. Like maybe you were thinking, oh, it's going to be the same. So if you change dx by 0.01, dy is going to change by 0.01. Okay, that would only work on the line y equals x. Okay, all right. Anything else is going to be different. Okay. All right, let's do this last problem, okay? So here we go. Here's an expression that relates x and y's, okay? And when x equals 2, and I change my x by 0.05, how is that going to change the y, okay? So to get my, then that would be my dy. And so what I need to do is I need to take the derivative of this, okay? So the derivative with respect to x on both sides would be well, let me just write it, d dx of x plus y is equal to d dx. And this is implicit differentiation. So this is good review for your final, okay? The derivative with respect to x of x plus y, this would be 1 dx over dx, which is just be 1, plus dy over dx, which is equal to, and here we have to apply the product rule. So the derivative of x with respect to x would be 1 times y plus the x times the derivative of y with respect to x, which would be dy over dx. So this is 1 plus dy over dx is equal to y plus x dy over dx. And I would say there's not one side better than the other to move them to. I mean, there really isn't. But you want to collect all your dy over dx's on one side and anything that's not a dy over dx on the opposite side. Okay, so I'm going to move everything to this left-hand side because that way I'm going to get dy over dx over here. All right, so I have this dy over dx right here already. I'm going to move this over, so it's going to be minus x dy over dx. And that's going to equal the y that's on the right-hand side. And then moving the 1 over, I get minus 1. And then factoring my dy over dx out, dy over dx, that's, not equal, times, and this would be 1 minus x, which is equal to y minus 1. And now I got to divide by this in order to get the dy over dx. Okay, so my dy over dx is equal to y minus 1 over 1 minus x. And so when what I'm going to need to do is multiply both sides by dx, and I wind up with dy equaling y minus 1 over 1 minus x times my dx. Okay, so now what is this telling me? Okay, if I'm at x equals 2 and I change my x by 0.05, okay, I'm going to plug those in here, right? But the dy is not just dependent upon the x, it also depends on the y value. So what that means is I'm going to have to find the y value. Now, how do you find the y value? Well, you got to go back into the original equation and plug it in here, okay? So we know that x plus y is equal to xy. And so putting 2 in for x, that'd be 2 plus y is equal to, and putting 2 in for x right there, that becomes 2y. And so I could subtract y from both sides and I get 2 is equal to y. All right. So what's that telling me? That tells me when x is 2, y is 2, right? And so my dy becomes 2, because that's my y, 2 minus 1 over 1 minus 2. I'm going to put parentheses around that, times the change in x, which is 0.05. Okay, and then my dy becomes, this would be 2 minus 1, which is 1, over 1 minus 2, which is negative 1, times 0.05. So 1 divided by negative 1 is just negative 1, right? So dy becomes negative 0.05. Okay, so what this is telling me is, for this equation, all right, at x equals 2, if I change the x and increase it by 0.05, that's going to result in my y decreasing by negative 0.05. So one's going to cause a change in the other, okay? And that's important. I've never seen this on the AP exam, okay? It's just, this leads to something we're going to do second semester, okay? And it's fairly easy. It leads to us, it's called separating, okay? We separate the dy over dx. And it's also good review for implicit differentiation, okay? So that's one reason I went ahead and did this, okay, this lesson. All right, guys, that's it. We have completed one semester of AP Calculus AB. Da-da-da-da. All right. Yeah, I know I'm weird and tired. All right. All right, you guys. Hopefully you enjoy some of my humor. All right, you guys. Take care.